Can I have attention, please? Please take your seats. Bring your coffee sandwiches, etc. Prepare yourself. Okay, this next session is all about missions, and mainly all missions that are associated with Australia. So we have presenters which are launching satellites in their own right, ones which are building hardware for satellites, and others which are participating in different projects as well. This is a showcase, so we each have very little time, and we're just really going to flash up what we're doing to give you a feel for what's happening within Australia. I'm leading off, so I'll try and lead by example by keeping time. And I'll cut myself off if I go over time. I want to see that. Yeah. Okay, start me rolling. Right. So, in this context, I am the project manager for University of New South Wales using CubeSat, 2.5-inch CubeSat, and EC0. EC0 is not one shot. It's one of those typical engineering names which stands for educational CubeSat. I will give you the briefest of overviews about what this entails. So we have had a seminar, presentation on the configuration. That's a refresher memory. We are part of an international consortium of universities led by the Primary Institute out in Brussels. We have put together 50 CubeSats, 40 of which will be carrying on board their science payloads. We have one of those that are carrying on board the science payload. We've been supplied with highly neutral mass spectrometer from London. We've been launched into a very, very low altitude. Not quite through there, not just from we come up down, so about 400 kilometers in a sun-synchronous orbit, and we'll be operating for a number of days until our altitude grades in the atmosphere, heat up and up to become 580 degrees. During that time, we will be continuously running experiments, both for the Compound Institute, doing their LMS experiments, but also we're carrying on board some homegrown payloads as well. Which will we're launching in February 2016, that's the hard deadline, which will take the time by the European Commission, which is very good. Just look out when the funding runs out. And we'll be sharing a ride with the F-49 up at CubeSats and running different things. Ten of those CubeSats are doing completely irrelevant to the industry goals, and they're doing I think quite a the engine, and fully other doing satellites with our design concept is we have used lots of components that commercially available off the shelf components where possible for our subsystem. So most of our subsystem components come from the space, and that has our benefit for us that we don't develop tools in the house, that we don't have to. We don't forecast the concentrate on the payload and also assist engineering. Configuration of our satellite is what's called shuttlecraft configuration, which is really, really good in the orbit that we're talking about. So they're in a low Earth orbit, and we need to be putting very, very securely with pilots. By having these solar wings, we use the small amount of air that's present to keep us working in the right direction. We are still fully three-axis attitude controlled as well, but this just helps to keep things capacity stable as well. We have payloads provided both in-house from the Space Center for Research and also from our partners, Discovery Road and NICA. NICA is developed an operating orbit which is naturally robust and fault tolerant. It's fantastic because we're up in a radiation environment and helps happen. And investigating this is one of the good aspects of CubeSats. We've tested this technology to increase capability. So actually, we're running two more pilot boards. We've got a GPS receiver, which is developed in mass, because something really easy to develop. And we've also got an FPGA board, which is also developed in house and executes follow operations in space without any population hardware. So there's pieces of the various boards and some of the specifications. So the memory is still forward, which is single the operating system and that's we have Rush, which is working very well. And we also got another experimental board, which is not a board. We're flying a 3D printed thermoplastic structure. So we're testing that rapid manufacturing technique. As a advantage of that disruptive technology in this market, demonstrating the cost of users. Good thing about that is that we have to do very, very complex structures, which have got optimized load paths, reduce markdowns, and the outcomes, there's all sorts of incredible outcomes. We're working with research here, and also raising technology, the components. Right, so that is one of the primary points of this for us, is we're getting our hands in with the CubeSats. It's no new people satellite. These are fully capable satellites. We've got all the subsystems for the normal larger satellite. We press down into the point of time on the little ball cracker. So we've got all of the systems engineering problems on the large satellite, compared to interfaces and control of specifications requirements. But you know, we can get hands on to work with. Okay. So that is what we're doing. So that's our showcase. We're planning some experiments. We're planning to do the history network. We're flying it in February and operating for about 6 months until we're going through that. Any questions about the Yes.
How did you originally get involved with the QB50 project?
Okay, it happened about 3 months before I joined the team. So,
I ran into a bloke from Mala who was all like that on his way to but there's something.
he put out a score, they went out and expressed the victim. I think on the name, he said that we've got so the money is right now, is what we use to make sure that easy. Okay, no more time for questions. I'm myself off. I'll bring up the next presenter. Okay, Professor John from University of Sydney, doing their I-Inspire 2.
Okay, I'm Joe, and I'm also talking on behalf of the team. So these slides mostly come from either, so I'm I have to tell you about our I-Inspire project. The instruments and devices we're installing on it, and I-Inspire 2, which is meant for a 3D project, and there will be a summary slide. So I-Inspire stands for Initial Integrated Spectrograph Imaging and Radiation Explorer. One of the intentions is that it's a Seoul University space project. And the idea was to develop a bit of space capability and I guess a little bit of PR as well. So the idea is to demonstrate that we can design, build, test, and operate such a device. Moreover, we've got a novel spectrometer, a little optical emission detection spectrometer for space observations or Earth observations. We've got radiation detector, and I'll show you in a moment. For space weather and other things. We also want to test the spectrometer for things like the effect of Cherenkov radiation, optical fibers they pay, so that sort of background test is also on the card. And for imaging, etc. So what's been the progress so far? There's been flatbed tests on breadboard, on PC board, and you can see the dates there. There's been an integrated system. There's also been a balloon launch. You can see all this is both in 2012 and Project Forest. There's a provisional radio license, and I think that the international, the overseas launch is underway since July 2012. Okay, so here are some photos of some of the guys working there on the on my Inspire. That's the balloon launch. There's Libra right there, playing with the balloon. And this is the canister, which the whole thing went in, and you can see Sergio and Chris there installing the canister. Yeah, so I Inspire 100 is intended to test the payload in I Inspire 1 has a small spectrometer and called nanoscope. They've got a radiation counter and an imaging camera. So that's the payload. Beyond I Inspire, which I'll tell you about as well, we intend to test a small plasma cluster that we also developed for the propulsion of the satellite, and a plasma wave receiver linked to space at the moment. So here's the nanoscope. It's just smaller than the size of the car. Has reasonable resolution. That's an off-the-shelf camera. Probably no better than a webcam. That's the radiation detector. All developed in-house. There's the optical fibers coming out of the nanoscope. They just point every which way because I Inspire 1 has no propulsion, it's just going to crumble. And so they'll point in all directions and hopefully get data, spectroscopic data from Earth. So there's some specifications of the spectrometer. You can see it's in the visible range. It has very reasonable resolution. It can look at the Earth for about an area of 40 square kilometers, and it's quite cheap to develop. There's the Geiger counter. You can see it next to a Cesium 137 teaching radiation source. You can see some of the pulses, very well defined pulses, easy for microcontroller to actually count. The thruster. I can't show you the thruster. I'm telling you about the thruster, but I can't show you because it's been developed in conjunction with the SDL. It's a tiny thing like that. And it packs a little punch, quite a little punch for its size. I can show you the spoon. So what you see there, the spoon sitting on the table. So that indeed is what you see. And so it's plasma thruster. It packs a little bit of punch in order to see the satellite maybe a bit more likely forward. Patent application has been launched, still waiting for it to be approved. Plasma wave instruments detect thermal manual waves to get electron density and temperature and to be able to measure magnetic field. So this is very much people can the domain where it's swing space together. Okay. So I Inspire 2, which is linked to the QB50 project, has passed a critical design review. It's a 2 spacecraft. It has a nanoscope, plasma cluster, the radiation counter, and active control of the magnet focus, and the latest stone. That's it. This is just a summary slide in case there's been any thoughts on the right one. I think that's done.
Thank you. Right. Our next speaker, Matthew from Adelaide, Matthew's QB50 build as well, CubeSat.
Thanks, Andy. I here to talk about our QB50 contribution to CubeSat, and unlike others, I kind of went in the opposite way. I went down 2 things that were really interesting to move up the ADTS system. I'm going to present them here, so this may kind of be a little bit out of context, but you know what the QB50 is about. We built, we didn't go with all COPS hardware. We developed our ADTS system, our comm system, our structure, and our secondary payload ourselves. And then the other side was off the shelf. So this is just 2 small aspects of one of the subsystems that we developed. So no time for an outline, I'm afraid. Just want to acknowledge the two students who had a lot of major contributions to this work. So, CubeSat on Cubesat mission, as we mentioned, and the orbit is 380 kilometer years time synchronous. So, I don't know how many people know that orbits in general, but they talk about a sun synchronous orbit, which means basically that the sun, your orbital plane changes as the sun moves around you, so you're at the same angle relative to the sun. But then you can either be supposing that's the sun, and then you can either go around this way, so that you go to right, dark, right, dark, right, dark, or you go around this way, you're always in the sun, the sun is always shining on one side. So, going around light, dark is called like a 12 o'clock non-cube mode, and going always in the sun is sort of this broad blast is called. So originally it was supposed to be a 12 o'clock mission, which means that you were very power restricted, so when you were in the lowest power situation, we would basically have around 2 watts, which sort of drove all of the design decisions. And also sort of thermally, of course, the difference is hot, cold, hot, cold, hot, cold. And then at the beginning of the year, they changed the mission and said, no, now we're going dawn dusk, so now we have more power than we need. We just spend a lot of money on holding the solar panels on the top that probably won't see the sun. We've got one sun sensor that also will never see the sun. So we've got plenty of power and we're probably going to be warm. But anyway, at least our design is flexible enough and we can cope with it. So that was actually a very important lesson that I mentioned in Masters this morning. Make sure you design your CubeSats so that you can handle any outland, which is what was on the slide, because that's what you're going to have to do. Anyway, those are our requirements. We've got a separate rate and then basically a pointing accuracy. So this is what our fine pointing system looks like. So first of all, we've got to know where we are. So we have a orbit estimation part, and then based on that orbit estimation, we know what the magnetic vector should look like. As in, so we've got a magnetometer on board, and we want to compare it to something. So we've got to know where we are, and based on where we are, we should know what the vector should be pointing, what direction the vector should be pointing. And then we can measure the difference and then see which direction we're actually pointing. But if you got just a magnetometer, you only have 2 of the required pointing directions, because of course you could roll around the magnetic vector and not know. So you have to have another piece of information. So we have a sun sensor, which then tells you that's the sun. So now all of a sudden you've got 4 pieces of information and maybe 3. So now you've got to kind of combine them somehow to make them into something useful. So you use a Kalman filter, and there are a number of different, there's a Kalman filter, an extended Kalman filter, and an unscented Kalman filter, which is the one we're using. And they're just different, just sort of handle different amounts of non-linearity in the system. And we also have a gyroscope, which is essentially a big reference system, of course, so that just doesn't have any absolute reference, it's just the only way you can use is to count how fast what angular velocity is, and use that from an own position and project it forward. So we've basically got those 3 sets of sensors, and we've got our orbit estimation. And then based on that, we have essentially we can work out what our pointing area is, and we use our PID pointing controller. We have 3 magnet filters and 1 reaction wheel, which reaction wheel to adjust the voltage. So I'm just going to discuss the part of the top first, which is the orbit estimation. So first of all, why do we need an orbit estimation? And that's because we were in a very power-constricted environment, and we didn't have enough power budget to run the GPS 24/7. So it's hard to run it sometimes and then not, and then turn it off. And the way we would do that was to develop a orbit projection algorithm, which in fact is also used on the space situation awareness project that we're working on as well. So this is just for the SGP4, it's a fairly standard one. So essentially you take the position and velocity from the GPS, you convert it to orbital elements, then you project the orbit forward, you convert it back to position and velocity, and then you rotate it to the required frame, and then from that you can work out where you need to be. So the problem is that when you measure GPS position and velocity, because the models that they use to develop the GPS positions and algorithms, your orbit parameters actually vary. So you have to somehow consider that and get a mean from that in order to work out what the orbit parameters are to project it forward. And if you don't do that, you're essentially projecting it from the wrong orbit conditions. And now it's still that. This is shows our detangle controller, how we can detangle down to the required spec. This shows our pointing accuracy when we got the site, and you can see that that's the upper bound, so we're within spec for that. But the interesting thing is when you go into dark, then you have no active reference anymore, you're using the dial anymore, and you drift out of spec, which is obviously a problem. So we had to then introduce a Linear sensor, something with some active reference point when we're in the dark. As it turns out, now we're not going to be dark very much more, so it may not be necessary, but nonetheless, we've gone that far down the development path that we're carrying on. So, yeah, basically, I presented an auto propagator, fine pointing controller, and the results show that in eclipse space, we need to have another reference point and develop an Linear sensor, which is just an infrared based sensor. And that's it. So I just put up our systems analysis is developed in core that ties all our requirements to our functionality and our hardware to do model-based system engineering. So with a good question try. Any questions? Okay, that's it.
The next presenter is Anthony Horton from Australia's most common facility, AAO, talking about Australian space science. So it's also take from the imaging from space.
So yes, I'm here to give a very good introduction to the space science. I'll do some questions. So, this is a proposed astronomical space telescope that was on the CubeSat. The aims of the project started with the camera to demonstrate scaling capability to CubeSat. Secondly, we want to develop capabilities that apply for astronomical research CubeSat missions. Secondly, we're looking at version. Developing capabilities, we want to use them to improve the performance of proximity and telescope objects. And with those capabilities, we want I don't have time to explain what this is, but we want to measure graphic background is science in nature, and we want to also image those guidance structures on the outskirts and our galaxies. Really data from the galaxy information. So the project, we're looking at funding on the LCD plan, and really use the Australian Space Science a good representation of Australian universities, each locations, and also we partnered with Poly, and the CubeSats, and the spin-off company, Driver. And so it's based on a 16-inch CubeSat platform. We just alluded to the prospect side, and it's based on the flyback endeavour platform, which is a highly integrated spacecraft bus, including all the standard spacecraft functions. And so, just to that, payload, most of the flights requires telescope, tracking telescope, microgravity, the focal length, and that is illuminating linear sensor from baseline into the CLS 105 CMOS sensor, and we are taking the picture of something in the sky that is view a little on the field where you sky. And with the telescope, we want to do deep imaging in the action of this aircraft. Meters into the long way down the Now, the main challenge with doing astronomical imaging in a CubeSat like this is practice work. So in order to also come into all these visible, those like targets, and especially when you have a telescope, you need to use long term for and you need to retain its stability and the duration of that exposure or deliver it so it's basically so this is something that you can't just really let go of. But what we're going to do is follow and develop or the exoplanets. Another astronomical CubeSat mission that MIT and CubeSats working on. And the approach is basically to start with those are the direction moves. And essentially start happening in the telescope over plane, so one over I spoke to see measurement, and then feed an information back into a we're also into a high frequency image stabilization system that uses censorship and flat, physically translating the range to take out the high frequency. Okay. So that's just for scale. Maybe it's supposed to be just try to see the space right. So at the moment, we are on the defense mission is being done operation. The process is a long one, so we want to know that we can turn it into October and November of this year, and we do that under. Yeah, then we will kick off the design build phase. We have 2 years, so complete by 2017, and look to launching from 2 years, basically. Keep going with what you can into small steps.
How will it compare to the other one?
Yeah. It's actually because of the way it's on things because we're looking at extended it's very low stuff and interestingly in other dimensions which the system is based on a single camera system taking that time. You need to make the one, but when we're going to understand the people.
I'm taking a little bit.
Thank you. Next presenter is Brett Martin from ANU, talking about CubeSats, which is a spatial biology CubeSat.
Well, the great thing about the name is if we drop the high altitude, it just sucks in the way it works. So what I was talking, our planned mission is fitting a science space around the CubeSat. Yeah, I know it's like what we're trying to do is use pretty straightforward off-the-shelf instruments to build and fit a high-quality science mission. So when we think of doing astronomy space research, there's pretty much 3 categories you want to look at. Either opening up a new wavelength regime, so something you can't do from the ground, like ultraviolet, doing high resolution, which the Hubble Space Telescope is quite known for, but also continuous monitoring. Since you don't have the pesky sun in the daylight, you can do 24-hour monitoring and actually get more value through your telescope. And if you want to look at specific targets, you can continuously monitor it and find it, such as new planets. Now, in terms of current and most recent ultraviolet missions, there's only really been a few. the Hubble Space Telescope, as what Anthony showed earlier. Now, he failed to mention it's just extremely hard to get time on this, so no one really bothers. Galax, which worked really well, poor resolution and died, and Swift, which is badly designed. So that means that if you can develop a ultraviolet space mission, there's room to make an immediate impact. So one of the things we came up with was building a wide field, high cadence ultraviolet satellite. Now, the inspiration of this was the Kepler Space Telescope, which most people know for finding exoplanets, but that worked in the optical. So if we can utilize ultraviolet, we actually get a lot more science we can do with it at the same type of thing. Now, the reason I had the high altitude part, the non-sucky part, was because you can do ultraviolet as long as you're above the ozone layer, which is between 30 and 45 kilometers. So if you were to fly a high altitude balloon, this is possible. Now, we've come up with a design that uses an off-the-shelf camera, so it operates at about 200 nanometers to 320 nanometers. So the what we call near ultraviolet phenomenon. Now, we want continuous monitoring. Well, we can actually use the natural orbit of a CubeSat to do the monitoring for us. We don't have to worry about pointing. We don't have to worry about stability, like Anthony was trying to solve. We just use the natural rotation of the satellite, natural orbit, to do our pointing for us. Because we just want a large area to do monitoring with. And if we can use the natural orbit, then it kind of solves it. Now, our other problem with this is we'll have an enormous amount of data if we plan to take 15-second exposures continuously for a year or two. So we're partnering with Google as part of both developing a satellite and also a balloon capability to help us with not only the data download, but also the data processing, since Google knows a thing or two about software. And it really gives a possibility of this mission actually going. So one of the things what we can see, if we have something that's monitoring ultraviolet every time, we can actually see a star blow up, but the shock wave went through the star before it blows up. Now that's cool to think, or we can actually see it hit another star. Now the reason we actually care about this is that shock wave tells you everything you want to know about the star, so it helps us know about solar physics. But we can use this in cosmology, or figuring out the big questions that when people know about horizons. Not that I'm going to win one. So, for example, so this is an image that we've done with the Kepler Space Telescope using optical. And what we're actually to detect is we're able to detect the shock wave down to stars less than the sun. So, those who don't know astronomy, there's not many stars out there that small. And this is just using optical, where it's pretty poor. We use ultraviolet to actually extend and do a lot more interesting things with this. So this paper is just accepted in Nature. You're not supposed to see it, so if you don't see it. Now, the reason we're actually doing this is something called Type 1a supernova. Why we care about this is what won Brian Schmidt his Nobel Prize. He used these to discover the universe was accelerating, and therefore was awarded the Nobel Prize in 2011 in physics. However, we realized after he did it that we know nothing about what we're using, which in astronomy never stops you. So now we're actually trying to go back and figure out what it is we're using to try and refine these measurements and hopefully figure out what is causing the universe to accelerate. Now, if you can do this with a poorly performed optical telescope and do it better and monitor large patches of sky, we can find tens of hundreds of these features per time and really take into the next step of what we're doing in cosmology. As an aside, we can also find interesting things. So in here, again in the optical, but the ultraviolet will be even stronger, we've seen the recombination of hydrogen, helium, and carbon in the supernova explosions. We can actually pinpoint how elements are formed in astrophysical explosions. And in astronomy, we always throw up the mysterious factor. There's a bunch of stuff things you can do with this, including probing and finding new planets around other stars, but finding them by detecting their atmospheres, and therefore what is actually going on in that planet. So instead of worrying, are there aliens there? We can just know, no, there's no aliens there. Aliens give you funding, so I can include that. I'll end there. Thanks.
We have time for questions. Go behind the mic.
obviously you're looking out. What's the possibility of having 20 meters out the same height looking up? Then you kind of have a pedestrian in a sense.
I mean, if there's a reason to build, the other end of the telescope, looking down and continuously monitoring it, like, who's the defense person here? I mean, really, we should ask the CIA about that. I don't know. I don't know what kind of science or interest there is. I don't see why you couldn't build in, kind of a polar telescope, essentially. That's not our interest for it. With the balloons, it's purely to fill out. If you have a high altitude balloon flying, you're actually the satellite or the platform is that other end. If you're flying something, in this case, Google wants to fly a few things, you can have a telescope pointing down in this case, or up in this case, to do the kind of complementary science.
Well, I'm just trying to get that.
Yeah.
Yeah,
You're tracking it down, exactly. Right. Yeah, I mean, it's a good idea. I don't know. Maybe better version of Google. It's an imager, so it's a one band 200 to 320 nanometer imager. We're in a one band operating from 200 to 320 nanometer. Okay.
Is that next speaker? Again, sorry, talking about altitude 1, which is a slightly different format. We're talking about quantity format now, rather than CubeSat, which I'll quickly do a demonstration side by side.
I'm Stuart from Perth, and introducing Western One. It's the first time I've talked about Western One project, so it's the 7.5 minutes to zero. So it's a 1 pocket cube in Australia, it's a solid project at the moment. It's the first activation satellite, so overview. Mission goals are to easily specifically Australia, but on the whole hemisphere. And the down version is to program to individuals. The second edition is it's a tech demonstrator. I say gold tech demonstrator because it's just using commercial. The other one's exploration. And there's only a few universities and organisations in Australia that could say that. Also, it's another very happy university to do it. So what's the project group? It's a pretty much a CubeSats. So I put 2 unit properties the concept created by Professor Briggs in 2001, and it was designed as a way to make space more accessible and accessible and so the cost of everything is relatively clear, so it's something like service and just the cost of the jet. As the last thing said earlier, the first property is something called the network working. We're at the technical level, we're actually on board with the CubeSat via. One of those four levels one of them is at facilities and so the total cost of that satellite is probably more like $250. To have something working for over 12 months in space for that kind of money. So possibly one is the typical small satellite subsystems. The motion, the ground system, it's all the attention to the energy system form factor that the energy design specifications for the so when I first started the build, I put it on one of the different cells, and I'm going to show that that's the button used in small cells, inches. So that, that's why we can decide range use them for the final question. The pizza serves were actually made by one of the first applications screen. I've also been used for like small triangular cells that you see on the CubeSats, but actually where to stop. So maybe give you a on see what the use market is a company that not quite as big as the triangular cells, but again the reduce those cells. EPS. So what the boards and the subsystems are going to make on so so HB Japan for package. The hardware is used the same to that, so it's the same IC to nothing the single IC for patent control and the and we'll probably make it so that has a very low component with the size and salary so small. Actually incorporating what we do with the brand output and system. And the next important is the whole unit. Point about handling is using the whole component. So for testing it, we create adaptable, we just use a little argument network controller. We have an operator type for storage of images, an open counter, possibly a non-active side but we no longer have to do this here for the communications. Actually, the project will be like us, the bypass the and the first one, transit module, that's all pretty much the $1 radio. And it's going to provided information to the receiver. The 1 watt transmitter is huge. Oscar, so I'm just going to and the reception unit is just quickly by a USB module and energy control. I don't know for processing power, so I just use vibration. So this is just going down may include the main payload is an optical camera. This is the one that is camera. So the estimators and our cube also roll the and that does it's like our videos as well. So it's just going to be taking those images and so there's a picture of the stack as it is now. It's a novel paperwork,
You might mention the problem to take consultant to where you are now, where you can see the
November 23rd was the first of that. And then sort of range of following. Also, when discussing the concept and based on the range of focus and the impact, CubeSat is a very core properties in the video and understanding. So, you start working from there and then
Okay. Right. Very good.
Thank you.
Also, talking about velocity, we've got the slide talking about growth.
So, my name is Simone. I'm from Cubesat, CubeSat. We're probably the youngest company here today. So this is our official hello, and hopefully you welcome us into the industry. I don't need to explain the difficulties of getting into the industry. You guys who know that pretty well already. The fact that you need generous amounts of money and how to know how to even be involved in the industry, which is obviously inherent in the nature of the industry with the cost of risks involved through the contributions. But we do believe that this is a limiting factor for the industry's growth and also the potential public involvement and interest in the industry. At Cubesat, we think this is extremely detrimental with many possible perspectives, innovation never heard of, because people feel like they can't participate in the involved. We're combining this with a very straightforward and simple approach. That would be ride sharing. This isn't a new idea, this is actually how we afford most forms of public transport now, including buses, trains, and airplanes. So we're actually taking out to the next step, and this is actually how the public transport affords space in our land as well. When I say payload, I'll just clarify that the people who are talking about ride sharing on the launch vehicle side of things. I'm talking about ride sharing within the satellite itself. So what does CubeSat actually do? We provide a satellite platform on which people can share the hardware and software space available on board. We take care of most of the technical aspects, the testing, and the organization of launch, meaning that riders can just focus on their payload approach and speciality. This obviously reduces risks and costs, as the resources needed to go to space and get your product into space are minimized, meaning that low Earth orbit is becoming more within the realms of reach for a much broader demographic. Obviously, for our name and why we're speaking here today, we use the standard CubeSat model as our platform. We want to reduce risk for all the riders involved, with their first venture into space. So we're using this well-used, well-understood, well-tested model, and we're coupling that with off-the-shelf components that have space heritage. The beauty about this model, I'm sure you all know because you're all the enthusiasts about it, is that it's basically a blank page that you can color, adapt, and alter to suit the requirements of the payload. So besides space-proven technology, we are making small innovations along the way. One of those innovations which I can tell you about is that we're launching the first Raspberry Pi on a CubeSat. On the Raspberry Pi, we are running your code from space. And we're actually working with the creators of Raspberry Pi and Microsoft to provide a familiar, simple, and fun platform from which you can run the software. In terms of the launch and orbit, we're being more flexible in these early stages, with allowing flexibility towards the requirements and timelines that the main payloads require. Regardless, we use obviously a launch vehicle with a good flight record, obviously because there's reducing risk everywhere we can. So what we're doing now, the sounds will vary all up in the air, and it's not quite that bad. We're actually in the midst of finalising contracts with UTS to develop and launch their first CubeSat mission. We'll be working closely with their students to develop useful and interesting payloads, and working closely with them in order to give everybody a fun learning experience along the way. By the end of these missions, Cubesat will have enabled UTS students to be, if not the first, one of the first set of students to launch a satellite into low Earth orbit, which is a great feat on its own accord, but that's also heightened because UTS students currently don't have access to a space program like other major universities in Sydney and Australia wide. During these missions, what Cubesat is doing is opening up the door to this range of innovation and ideas that have never been used before, to the people that have never had access to space before. We really want to reinvent the way that Cubesat is used and its capabilities, and by doing this and giving access to these people, we are hoping to involve more of the industry and develop much more of the technical people, and really grow the industry into being sustainable with the really much being outcomes for everyone in this room. Anyway. Yeah, and so what we're doing is we're just basically giving work with the technical people, access to a much broader spectrum of society to low Earth orbit. And the way that we're doing that is by taking advantage of the really simple CubeSat model. That's just a brief overview of us. It'll be a secondary payload. So, yeah, it won't be the main concept. Otherwise, it'll be secondary.
Right. Continuing on the theme, actually, I think it's all right. Of commercial access to data, there are some 25 CubeSats. We can ask some people who let go to these CubeSat programs.
Hi, everyone. Hello. So, just a couple of quick comments. Just an amazing series of presentations we've just had. I would like you to look at a lot of the technical IP that we've just seen in the last few presentations and think, what are the commercial applications coming about? And then I'd really like to have a think about the presentation we just heard from Mr. Lounge. Really, that is the future of the industry. Young, entrepreneurial company taking on the market, putting out a hypothesis about where the customers are, where they make their value. And we all need to be exposed much more to that environment, which the digital industry is saturated. We're going to get into the program in space. So I'm going to take you through a few slides that some of you have seen before. I noticed a lot of fresh faces in the audience since this morning, so I'm going to take you through a few of those slides. So Delta V, we believe that the space industry is broken and it's not working for most of the players in the industry. On the left-hand side there, the traditional space companies are not seeing anything like the growth rates you would need to sustain an interesting and exciting workforce with. We're not seeing things happen very quickly. We're seeing incredibly high price points, very complex missions. It looks a lot like mainframe computer circular 97, whereby the industry is a little bit stuck and ripe for construction. In the middle, entrepreneurs, they look at that industry, they see how many hundreds of millions of dollars need to get involved, and they go, oh, this is a disaster. How am I ever going to even get traction in the industry? And as Solange said, you feel like there's no point, it's too hard. And of course, the general public see it as this exotic, space nuts. They're like Star Trek, woohoo, kind of crazy thing. And they have no real way to relate it to the fact that every plot that they use, every ATM statement they get out of the bank comes from GPS time in spacecraft, that the weather forecast that they get at night, or that cyclone knowing they've got has come from spacecraft, or that the water management and land management programs and ocean management come from remote sensing data. People don't hear all those words, they just hear, that's science fiction. So we need to change that as an industry, otherwise it will stay broken. If we compare it to the tech industry, as I said this morning, you had in the 1970s, you had a similar environment to this one in the homebrew computer club. where they had little components, little projects, this, that, and the other, things like hard drives, the early mouse, CPUs and capacitors and the first printed circuit boards. People were sharing those around, and what came out of that? The world's most valuable company that has the biggest bank account right now, $250 billion plus. So I think we need to take a leap from looking at this industry where and certainly the new generation of engineers see it as just like their own nature. They're natives to this stuff. So we've got to learn that in the industry. Otherwise, you have to old folks like us around. The thing that we need to do is see holding small satellites, which is very much part of the workshop here, for all the reasons we've been talking about. Low barriers to entry, rapid innovation, fail fast, actually, and making that a positive, not that, oh my god, my career's over. And driving that Moore's law effect where every few years we're doubling that capability, lowering the cost, maybe even in 12 months. This is the analogy. So you can find this is actually a Nat Geo diagram. You can find it online. The analogy is on the left-hand side, we have the mainframe computer, on the right-hand side, we have the personal computer, even the mobile phone sitting in your pocket, which packs hopefully 100 to 1,000 times more processing power than the state-of-the-art IBM system, whatever, from like 1980. So I think you've got to see that as things evolve, you might scoff at, oh, well, this is something important. They can't really find the processing power that you get from a range of a GPS satellite. I'm calling bullshit on that. Okay? And history is against that argument. As we've talked about, lots of people are looking to address this market. 1.9 billion was the estimate from, I think, at least 18 months ago now. So I'm pretty sure, given that in January this year, there are 2 projects announced around the 5 billion total investment for small satellites. So we're going to see this number rise and constellation and similar technology into the next minute. And of course, we talked a little bit about the fact that it's private money. So what is Delta V? Delta V, we see ourselves as a space accelerator. We aim to accelerate companies like Cubesat. We aim to take projects from academic teams even and find a way to accelerate them both commercially and technically so that they can have a longer term duration. We are a space missions and data company, as in we execute missions. We're a space accelerator programmer. We want to be like Y Combinator, where we introduce you to mentors, investors, and an ecosystem. We have a space mission platform. Our idea is a regular space mission to low Earth orbit. It's a 6U commercial scale mission platform. We want to return data and value to Earth. We want to have multiple payloads. Very much like Cubesat on a larger scale. And by doing that, we want to prove to major commercial customers that actually they should take us to build their whole spacecraft and constellations of spacecraft. And as an accelerator, we would also want to work with people like Cubesat, like Matt, and Launchbox, like others, and do a consortium where we can share customer projects, share expertise and knowledge to fly. Our model is, as we said, is a platform approach to lowering costs. We have a standard set of specifications, we have a standardized CubeSat, we do off-the-shelf launch with somebody like NanoRats, who we have a high confidence in terms of their ability to deliver the mission, and we return the data to orbit. We try and do this often. But I'm really sorry for the initial kind of sketch of our core board where we have OCS, we have reaction wheel, we have all these other elements that we need as a platform, as a service effectively to the payloads that will be in the vehicle, and try and define these as best we can. Here's our roadmap. We've completed an initial design workshop. We're going to start doing full assembly in the next few months, and we aim to do first launch early 2016. Right? We're talking about launching 2016. It's showing up in launch window for Australian CubeSats, which is so exciting. And then we want to keep going. Also, we don't want to compete with anybody, we want to collaborate with everybody. So we see that we're opening up certain market segments. We're trying to drive a company that's got a $50 million plus valuation. So we're going to try and quickly validate our technology and our business approach so that we can then take on global projects. Along the way, we hope to spin off and involve lots more companies and groups, and at the same time shift towards a sustainable industry. When we get these, thank you very much. Thanks, Grant. Thanks, everybody. USW Canberra is into probably the second year of a 7-year effort at the moment to develop the capability to move 13 low-cost space lines in space. To do space lines on the ground, we have to take our lab into the sky and we'll be able to do it regularly, routinely, at low cost. We're building that capability on a number of different legs. Some of them are engineering legs, some of them are hardware, some are ground-based science, which then gets done in the sky. We need a particular vehicle to use to build that capability. And let me step sideways for a moment. And this is a piece of Australian space flight awareness. A high fidelity, physics-based understanding of what space objects do in orbit and how they interact with their environment. Space objects, space debris are not simply cannonballs in a cloud, and every piece is the same, and every piece reacts to the environment the same. There's many things going in space, and there's very big stuff. One of the things that we are exploring for what is called partners around the world to step up to the challenge, raise the bar on the science of this. That's what we want to do. We want to do it with ground-based experiments, with ground-based capabilities such as the carbon telescope that we see here on the right-hand side on that method, and with things like neural experiments. So we're investing $10 million in UNSW cash starting this year over the next 5 years, on 4 missions. The first two, in collaboration with ECO, we're looking at at the moment, and I'll touch very briefly on those two. On the left-hand side there, you'll see that we are building fundamental enablers to be able to do those space missions. That includes a flight team which is rapidly coming together. And some of that flight team were at the Underwater Rocket Range 2 years ago, September 2 years ago. So our experience in Norway was mentioned earlier today. I'll say, if you ever get the opportunity to go and do a space mission from Underwater Rocket Range, be prepared for the most amazing professional group of people. Norwegians and that rocket range are fantastic. Hopefully you won't have the same experience on launch that we had, and come to see the video footage of that. We're building a flight team, we're building various capabilities. I'll give you some snapshots of that in a moment. We're starting with 4 missions, and I'll work you through those in these last few slides. Some of the enablers include a ground station. The first part of that ground station, and it doesn't look like that inspirational thing on the right hand side, but next to the field, we should be able to start receiving data from satellites. That's going on roof and campus. We have 2 thermal vacuum chambers, we have a clean room, we have a nice laboratory in which to do some of the development work, we do flat track work, we've got the first flat already. We're working in close cooperation with AFC and our stronghold, and we'll be making better use of their facilities as well. We have some free first mission missions, so it's on the NDA with and exploring with them what they are able to do with some of their data. They can do dragging digital movers, and they are doing dragging digital movers, and we're working with them towards observing their telescope, predicting their orbits, and in return we receive data from them, and we can put the space flight and awareness capability further forward. At this stage it's just an NDA, there's nothing more concrete in terms of plans beyond that. Together with the UNSW Kensington, with AXA, we've proposed an experiment on the ARI flight mission, limit the space flight and awareness, aerodynamics of satellites experiment. And we have flight number 1 years to go. It's a risk mitigation mission for the Buccaneer mission, which David will describe here soon, and it's scheduled for launch late next year. We are currently going through the process of acquiring the CubeSat for that, and by mid next year, we should have integrated a single safety base and be ready to do the service provider. The main Buccaneer mission will take place a year later, late 2017. Meanwhile, we're developing space-based instrumentation, and we aim to fly in 2018 on one and possibly two CubeSats. The guided laser instrument for measuring greenhouse gases. That will work as follows. Satellite going on an orbit around the Earth, receives sunlight passing in and out of the atmosphere, hits the guided laser light with it, and enable you to understand line of sight and interactive content of the species next to you. And if you get clever, the way you build up this, you can eventually build up an understanding of holographic approaches to the content of the atmosphere. In the fourth mission on our books at the moment, we're looking towards the formation of CubeSats. We have a vision already working on formation time early into the quantum formation time post-life will be over here, and looking to launch in about 5 years' time. The beginnings of capability for distributed sensors on autonomous self-organizing collecting of CubeSats. Thank
Okay, last presentation before the coffee break. And with regard to this, the other thing we're about to show that is very much this exception to the box.
Good afternoon, my name is David Lingard from the Defence Science and Technology Organisation, and I'm the project manager for our CubeSat experimentation at DSTO. So I'll just give you a quick overview of our CubeSat projects. The first project is called the ARI, and it's a collaboration across five countries, our main collaboration partners. So the Departments of Defence from the United States, United Kingdom, Canada, and New Zealand. The main thing that we're going to be focusing on there is launching and utilising a formation of 3 CubeSats, and we're trying to do some neat experimentation with that formation. So the first goal is just to maintain the formation initially, and if we can do some other neat experiments, that would be really good. So in terms of launch, we're going to have a risk mitigation first, a risk mitigation mission with the following reality point. So we launched that up to the space station in December 2015, and then hopefully we'll be deployed to the space station in January or February 2016. So the RE point is just a single CubeSat for risk mitigation, and SWAD is our main mission where we're launching the formation of 3 CubeSats, and that's due for launch in June 2016. So in terms of the Australian government and what we're contributing, we've been working in collaboration with ASA, and so we've contributed the Memory GPS, which has been developed here at ASA in collaboration with General Dynamics Corporation in New Zealand. So that has been integrated into the launch, so into the outer spacecraft, and it's a very neat system. So we can get differential GPS measurements from that system, really differential GPS in post-processing. We get down to centimetre level measurements of the geometry of the formation that we use to carry out those information, which is really quite neat, and we hope to try that out. The other thing we can do is just use the RE CubeSats as targets, because we have the GPS information. So we have quite a few operational and developmental space situational awareness ground tracking systems in Australia, such as the EIS system on Mount Stromlo and the C-band radar that's been installed over Western Australia. So we'll be able to try and track the CubeSats with those systems and see how that correlates with the GPS tracks. And for example, I guess we'll be able to use the laser just to confirm, verify how well Memory is performing, but also get an idea of how well those space situational awareness systems are able to resolve the 3 CubeSats information. The other thing that the Australian government is contributing is a ground station being built in Adelaide, and that will be part of an international network of ground stations with some in the US, one in Canada, one in New Zealand, and one in Australia. So with the RE, the US government is doing much of the heavy lifting. So the Air Force Research Laboratory in the US, they're taking the payloads and integrating them with one of their CubeSat buses.
and they're doing environmental testing. So the US is doing the heavy lifting there. With Project Up Here, Australia is going to do more heavy lifting, so the design, the build, and the testing of the spacecraft. And as Ross has said, we're working in very close collaboration with his team at the University of New South Wales, Canberra, to deliver this particular mission. And we also hope to use the facilities of the AITC that Mike Technical is going to talk about soon. So what we're doing there at the SDO, we're developing a digital high-frequency receiver with a digital signal processing capability with a payload. And we're going to receive signals from our integrated operational radar network. So we've got a network of over horizon radars that can use in defense to detect aircraft movements. So the CubeSat will be out in the far field with those radars, and we'll be able to collect some data that will be very useful for calibration of the drone system. Well, the way we're going to handle that, so we're going to focus on the payload aspects in terms of our development effort. You can see one of the interesting aspects, see the large pot-shaped antenna. So each of those 4 antenna arms is about 1.7 meters long. And so one of our challenges is how do we line that up and stow a very small volume initially and then deploy it once on order. So that's one of our challenges. So for that reason, because we do have a few technical challenges, we're going to have a risk mitigation mission launched in November 2016. And hopefully that will go well, and we'll have our main mission launched in November 2017, where we'll try to achieve our scientific and operational goals. I should say that with these 2 missions, we're very grateful to our US partners who are providing the launches, which is extremely helpful indeed. With the, you see out there showing the internals of the CubeSat. We're buying the bus, the CubeSat bus from a company in San Francisco called Companies Incorporated. So we'll focus on the payload development, and then we'll integrate the payload with their bus and do the environmental testing ourselves. I'll just quickly mention another thing that is happening in defense at the moment. It's called the Responsive Space Capabilities Memorandum of Understanding. And basically, it's all about doing R&D to get capabilities to warfighter quickly and cheaply. And so on the right-hand side, you can see all the participants, including Australia, quite a few European nations there. On the timeline, you can see that December last year, so quite recently, all of the signatures were gathered for this memorandum of understanding. And we've been having some workshops to come up with some candidate project arrangements that might be of interest to different participants. So I attended one recently in Los Angeles. Now, some of the topics have been put forward, you can see there. So I've noted the utility of small satellites, things like optical satellite communications, responsive launching range, which are quite relevant to this forum. Ground station interoperability. So various countries at the moment are just thinking about what they'd like to be involved with, what resources they have to put into these projects. And then there's going to be a steering group meeting in the Netherlands in September. So the steering group will endorse certain PAs to go forward, and then they'll be drafted, and then it'll probably take about 6 months for them to be drafted and signed for 6 to 9 months, and then the work can commence and the project development. So I just thought I'd let you know, so I'm the point of contact for that MOU. Yeah, that's right. And I guess that's one of the issues that came out in the BC workshop is, what sort of policy do we need to put in place to stop, I guess, the floor of CubeSats being launched into space that might quickly become operational and then basically become a hazard. And so the US put forward that particular PA, and the thing there is, maybe we need to make
the orbit mechanisms mandatory. So I think one of the previous speakers this morning said that that's something that he's thinking about, making the orbit mechanisms mandatory. But the other option is to capture the altitude at which the CubeSats can operate. So I think the whole idea of that is just to start to talk through some of those policy aspects. You know, what do we need to put in place to stop these thousands of CubeSats that might launch in the next 10 years from the packet to do operational systems?
Okay. Right, we've now reached the point where we can have another conversation. Okay. There's both male and female here and out. In the
Okay, I touched you completely about what that means. And that's what we do away from the next hour and a quarter. And we're really cool with the next session. Next session is all about business support. So we've seen across sectors what we're doing in terms of CubeSats in Australia. Now you can see what Australia has to offer in terms of supporting CubeSats. Leading off quite actively is Vic from AITC, looking at the testing and evaluation side of relevant CubeSat missions.
Good afternoon. I'll try and make this as possible. I'm from the National Observatory, which is part of the Australian National University Research Group on Massachusetts. Back in 2003, the bushfires came through in the White Place. We lost all our telescopes and all of our infrastructure. It's a good thing or a bad thing, depending on the good part of it was that we managed to get some funding from the government and the university to rebuild our facilities, and now we have a world-class facility that is become, it will be a national facility for use by everybody. So we design, build and manufacture precision instrumentation. We also manage the Australian share of the funding down the Cubesat partnership. We have the only space environmental test facility in the country in one location. We are hosting the Space Environment Research Centre, and our aim is to bring together industry research, defence government education, for all the players to concentrate and focus collaboration in this space. We have a strong heritage of designing and building terrestrial instrumentation, telescopes, and instrumentation for telescopes. Over the last 10 years, we've built the SkyMapper telescope up at Cubesat and Whitefield spectrograph for our 2.20 telescope. We built 2 instruments for the 8-metre Gemini telescopes in the Western South. And they are 2.5 tonnes. One was a adaptive optical integer, and another one was unified spectrograph. We're also designing the first dimension of the telescope, which is a combination of unified spectrograph and we have extensive experience in the design, build, assembly, and test of both terrestrial instrumentation and a number of us have experience in building space. In-house now, we have very good facilities for the environmental testing of spacecraft. We are, as I said, a one-stop shop for all of the qualification testing and the self-assessment you need to do your spacecraft. You can come to us and we will help you get through that. We have thermal back, thermal cycling, vibration, EMI, and about 2 months' time we also have pyro shock testing. We have mechanical shock testing of accidents. We also have other facilities, especially for energy optics. We've got the digital project and optical division facility, and for a number of other basically facilities that we will need to develop spaceflight. And we're continuing to expand our facilities to be able to provide support to the community. We also have an in-house expertise and capability in engineering for space and also for precision instrumentation. So if you need assistance in the engineering side or the systems side or the project management side or anything to do with optics, we can provide assistance to you. We have established a number of strategic collaborative relationships and we're expanding those. At the moment, good for the next year profile. We working, started working with them. And that opens up a whole range of possibilities further, and we've been mentioned. Provider of highly integrated now satellite facilities are very interested in working with us. They usually also MIT, which provide a number of advanced technologies that we can use. Our objective, primary objective, is always to provide the engineering support and the scientific support to our astronomers, to able to develop their instrumentation primarily for this field, but also to expand that to be able to do astronomy and space-based stuff. We are a national facility for the integration of contested space equipment, and we make our facilities available to anybody working in this field at a kind of cost recovery basis. We've got government-funded facilities, we're not out to make a profit, it's not a business. However, because it's government-funded, we want to make it available to everybody, and we do so at the lowest cost possible. And I think that is it. If you need any further information, please talk to me, or send an email to Naomi, who's overseas, and I'm putting these here, and I'm sure we can help you out. Thank you.
Mike, how big is your thermal vac chamber? What size of craft can you put in there?
I think we could have CubeSats. It's,
I'm sure you can get CubeSats in there.
It's, I think the maximum we could at the moment, without any modification, is 1.5 by 1.5 by 2.4 meters. Up to 500 kilos. So we can fit, but it's designed to be able to fit a CubeSat. With extension, as you know, we've got that cylinder we can extend out to make it play like it's
Okay. Now, as a rule, we take on the audience, and then the next on this is the proper, which is done.
Great, well done, really. I guess, hello, Jason Hull. I'm the director of Sabre Astronautics, and we are reinventing mission operations, trying to modernize it for the 21st century. This is a program in R&D we've been going around for about 4 years with us, and it's calling off products and services that we think would be very useful and helpful to you guys. So this is the problem. We all talk about reducing the barriers to entry to space, and usually that means reducing the cost of engineering a satellite or the cost of launch. And what a lot of people don't realize is that your operations actually account for the cost of the total mission. Now you look at this screen, you can see wow, a lot of data on that screen, and there's this kind of linear relationship to the amount of data you have and the number of people that can help. But I want you to stick yourself in one of those seats for a second. You guys have your own satellites. Sit right there. What you're looking for, you're waiting for one of those little words on the screen to turn red. That's red. It means there's some sort of a defect that you got that. It's kind of a scary proposition if you're doing this for a commercial reason and scientific reason, because on the downstream there's a whole bunch of people who need that data to provide to them that can't reach it, right? So two different problems here. The user experience is two-dimensional, it doesn't really work anymore. Satellites are becoming more complex. Smaller satellites means that you kind of perform multiple satellites means reduce the cost of engineering, but your ops are still more difficult. So imagine, if you would, you're a space operator using a predictive ground station project, affectionately called PIGGY. Forget about 2D words on a screen. Here we go. Oh no! Huh? This time, 7 minutes. Is it going to go? Okay. Okay. So, yeah, that's a shame, man. I have an overview on the website. Go to the website and check it out. Okay. So, instead of words on a screen, it's all three-dimensional. So, I'll just talk through a couple of the features. Look on the right-hand side, you see the sun. What you can see out there, you can see sunspots. We got live data feed from the Space Weather Protection Service out of Boulder, Colorado.
You can look at the solar flares, the directional component, where they are, whether they're pointed at your satellite or not. We have accurate orbital mechanics. I think we're within about 40-point accuracy in NORAD at the moment. And you can get total overpass information. You can use all these sorts of features where you're tracking space weather and looking at the effects that it has on your orbit, your perturbation, and your mission. So we're bringing in the space weather and the satellite system status at the same time. Full target connectivity with your ground stations and your mission operations. And you can look inside that satellite, you can open it up, look inside the guts of it, and really identify all the different components and identify any sort of damage that's on the satellite and the cause and effect of that satellite as well. So what we're talking about is if you go back to this, and you're looking at a whole bunch of words on the screen, that means we've got a ratio of about 2 satellites, 2 spacecraft in this case, and about 20 people to control it. A lot of commercial operation centers are much smaller than that for sure, but this is starting real space operations. Okay, so massively massively simple for the user to control their own satellite. Okay, everything's visual, everything's intuitive, massively simple to train, and this is important, to train the operator for that satellite. Instead of memorizing every single one of those telemetry terms, you can just look and see what's damaged, and you can look and see what's affecting it, and get suggestions for the type of defective question you want to make. Now, on the back end, there's world-class artificial intelligence that's able to track cause and effect of the damage of your satellite as it cascades through the system. And this is important. The stuff on your left is an actual solar flare, right? This is the 2003 space weather event. And the graph on the right shows the output from the model, which is recreated based on all the interior systems of the spacecraft. It says, based on that model, this is the cause, the root cause of the problem. So we're able to go backwards into your system, and now what that shows you is that the models for cause and effect are dead on match. Okay. So that gives us a couple of unique advantages. 2 minutes, thanks. We are the first in the world that's able to model cause and effect on spacecraft in this way. There are other really good researchers looking at this, but the difference between them and us is you don't need to retrain the model with their software. You typically have to retrain with others. There are time and variance solutions. So you model it once, and then 8 years later, the model should still be active. You can be testing it out. All right. Now, a lot of that big statement there. So I'll tell you a bit about us. We're a small company. Have a lot of technical punch. We've got folks who worked on the Hubble Space Telescope, software engineers from the ISS. We've got 2 PhD graduates from the Robotics Lab at the University of Sydney, and we got decorated officers from Army Air Force Space Command. We've got an R&D lab out in Sydney, and this is where we talk about using the product as a service, the packaging as part of the responsible space operations center. We got one out of Sydney, we've got another one out of Boulder, Colorado. And we're starting to get a whole bunch of customers on boards for both purchasing the software to use yourself or for using our operational service. So if you don't want to do all that yourself, you just want to engineer your satellite, give it to us, make sure that your satellite is very well taken care of. Okay? And it's an exciting time for us because we're about to release the software for an academic license. It's our first release for it. So if you want to understand how your satellite is working, if you want to teach all the mechanics of the satellite system, or if you want to control your own student satellite, this is what you really need. We've got a pre-sale at about $80 per license per semester. We got that sale going just over the next month and a half. Okay, so 7 minutes is a long time. Sorry about the video. Do you want to watch it all last second? Yeah, sure. It's fine.
Okay, so what's your place?
This is more interesting. Does that sound? Yeah. Okay. So, oh boy, sunspots data feed. We're talking big data. So we got the same data feed that the strong government gets. So you're looking at radiation storms and radio blackouts. This is really just space situational awareness type of stuff. It's really about minute we got about 150,000 stars from the Arcus catalog embedded in there. So if you want to do simulation work for attitude control, or you want to look at the thermals, you can do day-night ray passing straight from the graphics view of your CPU. You've got overpass information right there. So that's 5 ground stations. If you show you rows of the ground station that you have under control. And there are just some fairly pretty graphics right there, just showing the magnetic field models and the electron content. So what this is telling you, if you do have a defect and you're not using the full autonomous diagnostics, you want to do it yourself. This is showing you'll have a data set available in your spacecraft. Now we're also learning elevation terrain data, so if you're doing any sort of remote sensing type work, we have an okay, so what's really interesting to you, if you're looking inside that satellite, and there you go, you can open it up. If you look inside the guts, you can identify any sort of a subsystem that's damaged. And there you go, there's your solar code paperwork. Red is obviously bad, so that's a damaged component. And you don't see it in this now, but components in blue is part of the column effect. So it's probably not a great question. We also have a New York feather that's been flight tested on parabolic flight under the NASA flight opportunity program. So it's required to put a New York feather comes from the flight. Thanks.
Okay, let's take this. We have just a bit of time when you can do that software and
Okay, so I'm from the Space Plasma Home Corporation Division that is trying to investigate and I'm going to briefly about the development of excellent podcasts and the ethics of plasma process for CubeSats. Actually, we don't know now from the neighborhood of our plasma structure or excellent plasma structure, which was the start of the Bomba Excel and then IIC so 2 years ago, we realized that you have more launch opportunities. It's better to design the smaller structure, and this is the pocket rockets, the small radio frequency microstructure. We want to have it at low cost, very safe, low power, repropellants, and it works with a few tens of watts, and the pressure in the plasma quantity to the plasma gas. The pressure in the plasma cavity is a Q4. So effectively, you can electro-thermal pressure. You put the propellant through, you ionize this propellant, and when you ion it for the collisions, you heat this propellant with all its X-ray in the space. So we move to the first accumulation. At the moment, the RF power supply is not available commercially, and so we need to develop this. So pocket rocket is 2 centimeters in length and just 1.5 millimeters in diameter. So with the rigid structure, it would be maybe like an aircraft one. So you see currently pocket rocket against my thumb here, and you see the plasma field that is there. So we have a patent on this, and it is by Roswell Technology, and we have rights to do research and training. We've been doing this for 5 years. We are close to students and other students, and we are publishing a lot of the research. We are doing a test in a small simulation chamber, which is called Wombat, which is the alien campus. We have an industry partner, and we have measured stress and basically input, so basically input the fuel efficiency in the small space chamber. So now we're working on the integration of pocket rockets into one unit, CubeSat. So first, top left image there, you can see that we have a little silicon test connected at the bottom with a little valve, and we can start our plasma platform. So this is the $20 version, but if you have a lot of money, you can buy a valve from Moocs, and so that part is kind of sold to the market, so we won't spend more time on this at the moment.
On the right, top right, we see proper motor powering in space. Ignition is quite easy, tuning is quite easy, so it's working nicely and everything is fast. If you want to put this into a pre-flash, you could use batteries, and these are commercially available, like one government. And the official task which we are working on now is to design a small RF amplifier, RF generator, and make sure that this RF is going to effectively into your plasma. So to go into the plasma, you need what's called a matching, an impedance matching network, and we have reduced these from a few kilos to a few tens of grams. So this is network is working. And we have reduced the size of the amplifiers down to a shoebox, maybe like this one at the moment. But the core component is working this orange circle here. So our aim is to now really miniaturize everything and make sure that when it's flown in the world. If everything fails, all these golden components, you can still use this thruster as a contact thruster. So there's a backup plan. But this, once it's working, will be really, really low cost, and hopefully will be bringing more opportunities to extract. So, as we are university, we can easily go from TRA1 to TRA5, so this is the technology readiness level. And here's where I thought it's hard to go along the dotted line there to something you can drive. So, hopefully together we can have more opportunities and try and get more hardware in place. So in terms of propulsion, electric propulsion, many countries are trying to the technologies. This is going moving really fast, and it's a key challenge. I won't talk about the other stuff, so you can take that in the future, but we are trying to focus on propellers. We know that no one has yet developed this subsystem, so once this is developed, it will bring new opportunities and it will work as complex. So we are currently designing our soil technology here in Australia. We will work on 1.3 units, and hopefully if you do have opportunities for payloads, we will see how we go. And so I just want to mention that we have the Advanced Instrumentation Technology Center at Mount Cornwall. We are on the main campus at AU, and that is forum led person can go into Wombat. And in Wombat, it's very, very easy to do quick tests. Very basic to do lots of tests, open, count down, check something, things like that. So this is quite idea that's thrust balance. We have developed the best thrust balance that exists for this type of thrusters worldwide. So this is another key parameter. For other people to develop these, they will also need to measure thrust in RF conditions very quickly. And we have a bigger version, which is the Wombat XL, and this amulet is going to be all the thrust measurements. So thank you for your attention.
I'll take advantage of that. Alright, so next presenter is one of our own, so John Hughes, talking about our open structural analysis on CubeSat. So just wanted to go over CubeSat structure.
Hello everyone, and thank you, Christine, for the final performance. So I am here today to talk to you about my undergrad thesis. I'm going to be doing some experiments on Cube50. What I will be doing is working with another student, and we will be doing material testing on the 3D printed structure. I believe it's called the Nemesis on the satellite. Cube50 has some extra space and that's available, and we will be taking care of that just to make sure that we fully utilize everything that we could to get the satellite out there. So just to introduce it, we're developing this satellite. It has the 3D printed structure on the outside, and what I'm trying to do is monitor the performance of the material while it's in place. And I'd also like to characterize the changes of the material while we're doing 6 space and space and all of it. This data should be very useful for design of future spacecraft. And knowing generally how the material will react to such a hostile environment. So since this is a tertiary payload, we have quite a few restrictive design constraints. We have to have minimal impact on the CubeSat, which means that I can't actually test on the physical structure on the outside, so I have to test these things out. I was also given a constraint that I think needs to be power. This means that it must be all ground firm, which I will do on to the next. And I will be using minimal computing power and taking a few data points every orbit of that. So here's the experimental setup. It's very similar to, this is just really a basic solids experiment we performed in second year. Except in this, I'm expecting all of the material properties to change. So what I'll be doing is making a lax motor, which I'll be able to figure out the force and displacement by monitoring the temperature. And I'll use that to push a cantilever beam, which should give me results on the strain gauges I'll have to talk about. And just so you know, there's another student working on this experiment with me. He's doing vibrational analysis, and he will have a mechanical sensor on the outside, which will be able to work while the cycle is cold and the actuator is attacking. What I'm expecting to get right now, I would like to find the changes in the cosine ratio, the elastic modulus, and the shear modulus. I'm looking into other properties that may change, but right now I'm really working on the concerning code and space. And I believe Marty is working on a few other components that can test that out. So what is the significance of this? Well, it's a novel experiment. As far as I can tell, nothing quite like this has ever been done before. There were quite a few experiments done by NASA that monitored materials, but they did all of their testing on Earth rather than actually testing it in space environment. And I'm going to generate data on this material and help with future structures that go into space, as cube is a very attractive material. This particular type of cube is 3D printed using laser sintering, which allows designers to make new and novel geometries, and it can be produced cheaply and quickly. So it ties in with what everyone else is doing rather than price. And then what future work am I about to do? I just need to finish up with the last actuator. I need to determine how it will function in the temperatures that we expect, and determine how the elongation of force will change the temperature. And from there on out, all I have to do is make the components flight ready. I have a test actuator that I have almost ready to be tested, in about 2 months to get flight ready system ready. So hopefully, we'll be going out on the Cubesat in 2016. And I think I'll finish early so we can get to the program. Any questions?
Okay, our next speaker is also a timekeeper, and I said this is where my go forward involved. I'll send it along. Okay, fine. So again, talking about working with the non-pressure pieces from 2005. Confirmation to take missions from any of the people by aircraft, so we track aircraft over the ocean, becoming ever more popular.
Before I start, I'm just going to sacrifice some of my 7 minutes to do a shameless plug for Cubesat, which unfortunately didn't get representation today. What I'm holding is actually the first prototype of the onboard computer of the possible. So CubeSat, in the background of what actually we're trying to achieve with 50/50, is actually going forth and trying to create its own bus from scratch as an educational exercise to help undergraduate students develop and understand the LS system. So if you have any questions about this, feel free to come and ask and actually have a look at us as well. It's a lot of flight models, so I'm happy for it to be touched and whatever. Anyway, that's the thing. So onto the actual presentation. Now, the whole point of, and this became particularly topical when the Malaysian Airlines flight MH270 was lost, was that we have no way of tracking aircraft when they go operations, at least in a reliable manner. And so the idea to try to solve that issue was to use, in particular, CubeSats to track those aircraft, since a new technology that I'll talk about a little bit later on in my presentation was introduced into the market as a mandatory technology for all aircraft to fly. So as an introduction into what the technologies currently exist, we currently use sort of 2.5 methods. The first is ADS-B or SSR, and those are very much the traditional radar technology. In SSR, we interrogate the plane, and then the plane responds back with a message saying, this is where I am, this is who I am, and I'm not currently crashing into the ground. The mobile data link is something that is used by more commercial airliners and isn't in fact in every single aircraft. So this is what happens when a Qantas 787 buys a mobile phone, a mobile satellite phone rather, plugs it into a modem, and then uses the modem data to upload that to the internet. And that's how commercial aircraft are able to track each other. But ADS-B is the one we're particularly interested in because in America, in Asia, and in Australia, it's being mandated as the primary and mandatory method by which aircraft report their status. Now, the issue with ADS-B. So, firstly, how it works. ADS-B relies on ground antennas that act as clients to how, when the airplanes go overhead, they can continuously broadcast all the information about where they are at the current point in time, and then that goes into these reception antennas, which then get transmitted via a ground data link to some air navigation service provider, some aggregate sensor that puts all of that data together and displays it for us. The issue is that we can't place these ground antennas over oceans, or over desert where it's hard to get a power line out, or over basically any piece of land or water on Earth where it's hard to get infrastructure out. And the problem is when you look at the most popular aircraft lines and the aircraft navigation routes around the world, you see that a fair chunk of them actually happen over water. The one that's one of the most highly popular corridors in the world in terms of international flights is hopping over the transatlantic flights between America and the UK. And when we compare that to, on red there, showing all the areas that don't currently have ADS-B coverage, we see the problem of airplanes not being able to track, not being able to be tracked. And this, of course, contributes to the MH270 problem, because it essentially disappeared over, it essentially disappeared over one of these red regions over here. So, the concept of the research that I went to was using satellites, small satellites, as a relay station, as shown by the crude MSK drawing that I have up on the slide there. The plane would transmit and point its ADS-B antenna up into low Earth orbit. That data would be aggregated by a low Earth orbit satellite, which would then transmit that data down to an Earth ground station. And if we put these satellites into a constellation, and an example of which is shown on the board, that's the Ingredient constellation, we're able to try to simulate global coverage, if not coverage of at least the problem areas where we don't have enough coverage of the oceans for those transoceanic flights. So after doing research into varying the various parameters that you see up on the slide there, and simulating various flights, all of those transoceanic flights in Systems Toolkit, we came across this satellite constellation as the most optimal in terms of a brief parametric study. So we have 3 planes of satellites. In each plane, there would be 6 satellites at approximately 700 kilometer altitude, and each of those planes would be inclined at 60 degrees and then equally separated out half the cover. These results are available online and in a journal whose name I'm forgetting at some point in time. If you see the afterwards, I will Google it. So the results that came out of this when I applied it to the MX370 test case was that during its time from liftoff from Apollo 1 4 to when it disappeared, we would have had 20 discrete data points of where the plane would have been. As it was, we lost track of the plane over that particular waypoint over there. But you see the coverage provided by the satellite constellation means that we would have been able to more concretely pinpoint where the plane was when it had disappeared. As it was, that point, waypoint, and that waypoint were the only two ground ADS-B antennas available at that point in time. And it's only for that reason that we extrapolate that a straight line of some sort must have been going between those points. And with the satellite constellation that I put forward in my study, it would have spent 10% of its time in the dark, i.e. without being able to transmit its information, and there would be a maximum gap of 5 minutes. So the plane would have only spent 5 minutes without being able to see a satellite, at which point, if the entire system got rolled out, an air navigation service provider would have been alerted to the fact that this plane had disappeared within a 5-minute window. There's some more future work to be done in terms of modeling the RF link a little bit more realistically. That's currently being done as a modest thesis by a colleague of mine, and then an end parameter study to actually try to figure out what is the most optimal solution in terms of numbers of satellites, inclinations, and altitudes that's being done by a separate colleague. And that's the end of my study.
One question.
What size of this satellite?
We did it specifically for a 2U CubeSat. So the antenna system that's being currently developed is being developed for to fit onto a 2U CubeSat.
As a background, to turn up some comments, two things. Okay, thank you. Now, our next speaker is a host from University of Newcastle, who is talking about the principles of CubeSat design and build.
Right. And I'll try and be quick because I've been putting on there a long time. Yeah, basically, I'm Andreas. I'm from a small coastal village with 300,000 around Newcastle. Here's a because of a project that I've been doing my electrical engineering part of the project. Basically, it's focused around really affordable CubeSat hardware. The motivation has come from basically this entire movement of why everyone's here, to make it possible. But it's got a bit of a twist. It's not the traditional hardware. I'm a single man team at the University of Newcastle, just like Stuart. Yep. And so basically, what I've been doing is I've been working on a power supply module, a telecommunications module, and a processing module that are important to CubeSat spec. But what we're doing is, what I'm doing is, I'm focusing on part of the market which hasn't been touched yet. And it's an immediate market. It's not a final solution. It's basically, in the middle, it's an educational platform. And it's basically centered around designing the hardware so that young students can help us involved. Right, so on top of that, what I'm aiming to do is to make it really, really cheap so that schools can buy it. And it's functionally accurate, but it also means that all the students that buy the hardware can do their full experiments in the tinker and do new stuff. They can even buy boards because they're so cheap that you just replace them. When they're done with that, and they understand what's behind actually making a CubeSat, then they go on to the new guys, like, Flight Space, Strong Space, Pumpkin, ISIS, and even a lot of the stuff that you guys have been developing and talked about today. So what else? When I said that they were like as functionally capable as conventional models, what I mean is they still have all the functions. Like they provide a extensive amount of primary power rails, battery charging from solar cells, multiple communications methods, and packet processing that's all built into the designs. And there's a basic microcontroller interface that basically is as simple as possible for students to get involved with. To build it, I've basically taken on the CubeSat as a whole, and these are some of the things that I've come across to try and make it as cheap and as robust as possible. Basically, firstly, I like to provide as many useful voltage rails as possible. So I've got 3.3, 5, 12, and primary battery bus, which allows for a lot of flexibility, and a lot of creative modules, assuming that the modules on the market at the moment. The microcontroller actually comes in two flavors. It allows for the MSP for 30 by text instruments or 80 mega. What this means is that students that aren't familiar with C programming and stuff like that can interface with Arduino or Nokia, which basically means that even a high school student could actually get one of these things up and running after that. I've tried to remove unnecessary modules.
June started to brand which was launched. So we put four satellites, the one is for one team, for one satellite. Struck the website which is still operational, you can go into the 15 months in orbit. And as well as, yeah, pretty simple story so far. The Vision was a Californian built satellite, and CubeSat was a mainland agency. They were deployed, so this is Chantal's on she was born in the South Africa. This was for cluster of groups. This people who were involved, but we did back then. There was a bit of effort, that's the launch. So that Chantal's launch to the next cluster. So this bit is one focus in Germany to date. Cameras, action pictures, access reaction rooms, code shading, both of the processors are flowing, based on sensors, a little bit of connect, and we're working a lot in terms of the next generation of prototypes, the next batch, as we're working out small papers.
up in this space industry at all. You know, your own work and seeing complementary activities that are going on around you, I think you'll probably be encouraged. Thank yous. First, I'd like to thank the School of Mining Engineering for letting us have their room at relatively short notice. We had to upgrade the size of the room once, and as it turned out, this one turned out to be a cramped as well. Thank you all for coming in. Such a fantastic response in terms of attendance. I think I'd like to thank all of the speakers. So if you'd just like to show your appreciation. Setting up today was not an easy task. Coordinating it has been very difficult, and that goes to show us. I think it shows some appreciation for it. So she was, last time I saw her yesterday, she was off to try and steal some chairs to fill out this room. I think the chairs in this room came from several different buildings across the campus, which we could pull off during teaching. Today we've had presentations from 9 different countries, several of them live, and I think the team that has managed to coordinate that, or Cheryl coordinated them, but the team coordinated that work. I think their work today has been, I think the team would be fucking awesome. I mean, seriously, to go as we have done today, pretty much without a hitch, is unbelievable. So, June, Jen, Tim, Sana, thanks, Barnaby, for sharing. Okay, next steps. Firstly, in terms of events, we would like to make this a relatively regular event. We haven't set a date for the next one, and I think we won't for a while. What we're thinking of doing is waiting until we actually have CubeSats in order. So probably Viari and QB50, when they have launched, then would be a good time to come back and talk to people who've got satellites in orbit, and so they can talk about their data and whatever. I would imagine there might be other people who talk today who might think they have something in space right then as well. So we can keep those. So we're thinking of doing something like that. Obviously, that's at least a year away, maybe a year and a half. I've been talking to Elias about his paper that he wrote today, or the presentation he made today, and we may try and progress that discussion about where some of the legal side of this should go. And I think the way we might frame that is a debate. We'll probably have that sometime between now and the end of the year. That may, this is going to we came up with this today. It may take the form of firstly a white paper that we might release. Elias would probably write. We may actually ask other people who have differing opinions to write them, and we'll get those people together to discuss where we should be going to make it easier, to remove barriers to people who are actually trying to progress in the industry in this country. Thirdly, later this year we're running the offer of mining board. He has already, but anyway, that's the sort of service I think to expect. So later this year we're running the second offer of mining board. The first one we ran in 2013, which was the most successful event ever run by the Faculty of Engineering in UNSW. By that I mean we had a media reach of 8 million people. We had a public lecture in the fancy theatre, which was oversubscribed, so it was full with 1,000 people there. We're, in terms of the public lecture, we're intending to do that twice this year. Keynotes for the Opera's Mining Forum, the project lead on the Philae and on the and also the project lead on the asteroid redirect mission. So we've got someone from ESA, someone from NASA talking about those missions, particularly the technologies that are relevant to off-Earth mining. Now you can see on the banner there that the off-Earth Mining Forum this year is being coordinated with the Future Mining Conference. So the idea is to get space people and the mining people, particularly the mining people with the money, in the same room. We're actually sharing a There we go, there's a minor. Trying to get them in the same room for at least one session of those two events. They're going to be co-located over at the technology park. And last time we ran it, we had trouble getting official representation from mining companies. This year we're hoping to do much better than that. Access website, please. In terms of progressing this CubeSat community ecosystem idea, the first thing I'd like to just point out is the new button. There you go. So now press the button. Right. So if you go to our website, there's a page that I have up this morning. If you just put all your details in there, we'll probably try and interact with you as a community to see what sort of events we should be doing next and how we can get this ecosystem community to forward, like working together in the way that we know that the UK groups are working. So please, take down the website, do that immediately. Now, the final website is the map of where we are and where we're going. Now, when you point to where we are, we're down the old main building, and we're going over to C15, going up. There it is. You can see there's only two buildings on this picture which don't align with the XY grid. They are the two buildings that are older than the university. So that's called the White House. It used to be part of the old racecourse that was on this site. They serve beer there. Please make your way to that facility for that purpose. And thank you all.
Do you guys want to head to? Thanks. You guys want to? I was going to head over there right now.